Okay, welcome to podcast 4.4c on diffraction, part of 4.4 wave behavior, part of topic 4 waves and oscillations. Diffraction through a single slit and around objects is a required understanding for standard level, as is qualitatively describing the diffraction pattern formed when plane waves are incident normally on a single slit. Keyword there is qualitatively. In other words, you're not actually meant to do any calculations for this. You're just meant to know what it kind of looks like and what is sort of happening. If you are a higher level student, then part of the topic 9 wave phenomena does require you to be able to apply some mathematics to this, and mathematically it's quite a complicated situation, but a qualitative description isn't too bad. So diffraction is the spreading out of waves at a gap or around an object. Plane waves, so waves which have straight wavefronts, approach a gap or go past an object, and at the edge of that object or through that gap they create generally circular patterns. That's basic diffraction. Here you have an illustration of that. You have waves approaching from the south, well, from the bottom of the picture, and as they pass through the gap between these two islands, these quite long wavelength waves, you can see this not exactly circular but stretched circular diffraction pattern being produced. Also note that around the edge of this island there is another diffraction pattern produced, and those two show superposition and interference, which we'll be looking at more later. On the right, you have an illustration of this process, a mathematical animation model. And to demonstrate why it happens, let's take this as an opportunity to do a demonstration of Huygens' construction. So remember that Huygens' construction says that any wavefront is a source of a wave. So just these little bit of a wave is able to pass through, the rest will reflect back. And we can draw some circles there with a radius of one wavelength, and it will illustrate the resulting wave pattern, which you can see is approximately circular. Then each of these wavefronts each of the points on this wavefront acts as a source of wave, which creates another wavefront, one wavelength distance, and so on and so forth. And you have a spreading out of a diffraction pattern. That diffraction pattern works best when the wavelength is approximately more or less the same order of magnitude and size as the gap. You get a nice circular pattern. This also happens, as I said, at an edge. So the bottom half of this picture, the waves carry on unimpeded, but at the top they are blocked and therefore they diffract around the edge. It works for a single slit. And then the final example for this little bit, if you just put an object in the middle of the path, then it will do that edge diffraction around both edges, and you will have a sort of region of confused, overlapping, superimposed, diffracted waves going around either side of your object. With light waves, you get to notice, I mean, technically you could get this with water waves as well, and it can be seen, but the conditions have to be quite unusual. Whereas with light, it's much more common to be able to demonstrate a diffraction pattern. Now, here you don't get that sort of circular effect so much, because if nothing else, even when you're talking about a very small gap of just millimeters in size, then you're going to get a much narrower wavelength of light going through. And what you'll find happening if you have incident light on a very small gap is that on the far end you will see a sort of diffraction pattern. Now this is kind of a graph showing intensity, if you like, of the light pattern that's produced, and rather than just being significant at the middle and then falling off, which is what you might expect, you'll notice it has this sort of ripple effect. It goes down to a minimum, first order minimum, and then up to a sort of mini maximum again, and then back to another minimum, and that's symmetrical on both sides. The reason for this, again, in higher level physics, you're going to have to go through and do the mathematics of this a lot more. But we can illustrate kind of why it's happening by Huygens' construction. I said that every point on a wave acts as a source of a wave, and if you have enough of those along this gap, if it's kind of the right sort of order of magnitude, then you'll have them interfering with each other, and some of those interferings will cancel and some of them will reinforce. You'll have destructive and constructive interference. If you put a screen there, it captures these points where there's constructive interference, both lots of it and sort of lesser amounts, but also the points where there's destructive interference, which result in zero intensity. Okay, so what does that actually look like? Here we have a couple of images showing what we mean, thanks to the University of Sydney for these images. And we have here a slit, lasers shining on a slit, and the width of that slit is constant, and the screen that these images are being projected on, these patterns are being projected on, is the same distance. But we've changed the wavelength, and you can see that that does slightly change the diffraction pattern that's produced. You'll see how the graph here of intensity relates to the image that you see. So changing the wavelength, red light, what light, green light, will change the pattern slightly. And here we have the same wavelength, so we're just using the red light, we have the same distance. What we're varying this time is the slit width. So these are very narrow, very narrow slits indeed. In fact, I'm not totally convinced by the NM. I think it's much more likely to be millimeters than nanometers. But you'll notice how as the slit gets smaller, the diffraction pattern actually gets bigger and wider. So a wider slit will tend to give you these. And once it gets sufficiently wide, those little gaps will kind of just merge and you will see a more what you'd expect to see pattern. Okay, so, before we go, I just wanted to demonstrate that light waves can also show a diffraction pattern at the edge of an object, not just through a slit. And here you can see that we call these diffraction fringes. So it has to be coherent, monochromatic, single wavelength, otherwise it gets kind of confused and messy, light. But under the right conditions, then a sharp edge, such as is provided by a razor blade here, can produce some very nice looking diffraction patterns as the light waves diffract at the edge of the object. So we have demonstrated diffraction through single slit and around objects for both water and for light, and we have qualitatively described the pattern that is formed. Thank you very much.